Okay, so this guy's name is pronounced L'Hôpital, and I don't know what language that is. I should know. Is it? Okay. Anyway, some people actually put an S before the P, so it looks like hospital, literally. But some people don't. So I've seen it spelled both ways, but that's the guy's name. And it's fancy O. What do you call fancy O? Not sure.
It's always circumflex.
Okay. This is the assignment for day 1 stuff. Again, it's not due until you get around to it, right? So it's not due until the end of the chapter. This is the rule. It's really a very simple rule, and it's basically how to solve a limits problem. So if you just look over this whole sheet, it's just a bunch of limits problems. But L'Hôpital said this: if your numerator and your denominator are both giving you 0, that's what this is saying, then you can try taking the derivative of top and bottom and plugging in a. And that might be the answer to your limit. In fact, he said it will be the answer to your limit as long as these conditions are met. Okay, so what we're going to do on every problem is the first thing we're going to do is just make sure that L'Hôpital's rule is permissible, because you cannot use L'Hôpital's rule on every problem. First, we'll double check that it's okay to use. Okay, after we check that it's okay to use, we'll find ourselves doing a little bit of derivative stuff, and then out pops the answer. It's actually really, really interesting and clever. So let's look at our first example. And we'll skip over the proof right now. I might come back to it later, just while I'm explaining stuff. Okay, so I've given this problem before to my pre-calc students, okay? And I actually had to give it to them with a square root, not a cube root, because the way I taught them to do it is to use a conjugate on top and bottom to remove the radical term, to eventually remove the x minus 8. And you guys also have learned to do it. So let me just show you what I'm talking about. I'm talking about those problems where you have like LIM, x goes to 4, and it's root x minus 2 all over x minus 4. And then you multiply top and bottom by a conjugate like this. And then what happens is your numerator becomes x minus 4, and your bottom denominator here becomes basically this. And then the x minus 4 cancels out. You probably remember that. And then you can plug in 4. So when you plug in 4, you just end up getting 1 over root 4 plus 2, so 1/4. So you might remember doing that, but it's notoriously difficult to do with a cube root. Like if you had a cube root x minus 2 on top, you would probably use similar principle, but finding a conjugate is fairly challenging. Now, how do you solve the problem using L'Hôpital's rule? First, you have to make sure it's eligible for L'Hôpital's rule. Not every problem is. So what are the conditions? We have to make sure that plugging in the a gives us 0 both top and bottom. So this is f of x and this is g of x. If you plug in 8 into the numerator, what do you get?
0 with 0.
Yeah, 0 on top. And if you plug in 8 in the denominator, you get 0 on the bottom, right? You get 0 on top and bottom, right? That means that this is a L'Hôpital ready problem. You're welcome to use L'Hôpital's rule for it. The only time this wouldn't work is if the derivatives don't exist. But these things are just polynomials and rational functions and radical functions. You should be fine with taking the derivative. So what I'm going to do is I'm just going to take the derivative of the numerator. So think of this as x to the 1/3 minus 2. What's the derivative of that?
1/3 x to the negative 2.
Right, 1/3 x to the minus 2/3. And of course the minus 2 has derivative 0. Then go down to the denominator. Find the derivative of x minus 8. What's that? Simply 1. And although this problem has changed, the limit has not changed. If we now do LIM x goes to 8, we get 1/3 times 8 to the negative 2/3, which is 1/12. So what did I do? I first recognized, hey, this thing is 0 over 0. And then I took the derivative of the top, derivative of the bottom, plugged in 8, and out pops the answer to the limit question. Interesting. Okay, so now let me try to explain why this works. This is kind of hard for me to explain. I did type a mini proof here for you. Okay, and it's really not very hard to follow if you read through it. But let me just try to explain what's going on. So the cube root of x minus 2, that graph looks like this, guys. And when you get near 8, you know what happens? It gets real close to the x-axis. In fact, it finally hits the x-axis at 8. Okay, so that's cube root of x minus 2. This is the graph of the numerator. And then the graph of x minus 8, of course, is a line. So let me color code this. Here comes a blue line at x minus 8. So here comes a blue line, like this, slope 1. This is the graph of the denominator. And out here at 8, the red and the blue collide. Unfortunately, they collide right on the x-axis, which is why we're having trouble with this limit. Let me move this over a bit so you can see it better. Hey, don't miss this. This is very interesting what L'Hopital figured out. Okay? So you see how the two curves cross right at the x-axis? That's why this problem is so hard to solve. When you plug in the 8, you're getting 0 for both curves. See? So here's what L'Hopital figured out. And I don't know how he had the insight to know this. But he said if you zoom in really close right here, okay? So let's zoom in. Look just at this region, really close up. Expand that. You see an x-axis, right? You see a red curve coming up through. And you see a blue line coming up through, and they actually kind of crisscross right there. And this all happens right at 8. And he said this. He said the ratio of the y-coordinates, the ratio of red y-coordinate to blue y-coordinate in here is the same ratio as the slopes are. The slopes of the reds and the slopes of the blue form the same ratio as the y-coordinates do, which is profound and amazing that he even noticed that. Like, how would he even see that visually? So the slopes here are approaching a certain value. The slopes here are approaching a certain value, you agree. And the ratio that the slopes are approaching is the same as these two distances are approaching, these little deviations from the y-axis. How did he know that? Anyway, he knew it. I don't know the history on it, but he basically said, look, I'm having trouble getting the y-coordinates in this area, the ratio of the y-coordinates, but the ratio of the slopes is the same anyway. How he knew that, I don't know. But you can see what he's saying. We just took the derivatives, and he's basically saying, look, the red line has a slope 1, or the blue line has a slope 1, and the red curve is approaching slope 1/8. So we can see that the ratio of the slopes is the same as the ratio of the curves. And that's very profound. But even if you can't understand how he did it, you can appreciate that he did do it and that it works. And look how easy this problem was. Just two derivatives, plug in 8. Okay, question or comment? So let's use this rule, right? All we have to do is make sure it's L'Hopital ready, and then we're welcome to use that rule. So L'Hopital ready means it's 0 over 0, in case that's not clear. Okay, so let's look at the next problem. Is this next problem 0 over 0? That means when you plug in the a value, does it give you 0 on top and bottom, both?
Yes.
What do you guys think?
Yes.
It does. Okay, sine 0 over 0. That's 0 over 0. So this is L'Hopital ready. And I usually like it if you guys label this. This is a 0 over 0 type problem, isn't it? So what you do is you just take the derivative of top and bottom. And although the expression is changing, the limit remains the same. So what's the derivative of top? Cosine x. What's the derivative of the bottom? So the derivative of sine is cosine. What's the derivative of x? Simply 1. And now you can plug in the 0. And there's no consequence. It's not like you're getting undefined anymore, or 0 over 0 type stuff. This is literally 1 over 1. The answer is 1. Now you saw this limit at the beginning of the year. We used limo sine x over x on our first test at least 3 times. Okay, you also saw it in pre-calc. Although at that time, Mr. Lynch or whoever taught you pre-calc probably had to just tell you that it's true, that this is 1, and not have any real justification for it at the time. Okay? Maybe he showed you the graph, which is very convincing. When you're near x equals 0, the y does appear to be 1. Maybe he showed you a table, and the y values look so close to 1. Well, here is your reason. L'Hopital's rule says it's 1. Very cool. Okay, now let's go to this next one. This too is one you may have memorized. It's actually in the state standards that you have this one well memorized. And the answer is 0. But why? Well, first double check that it's eligible for L'Hopital's rule. And it is. If you plug in 0 here and here, you get 1 minus 1 on top and 0 on the bottom. So this is a 0 over 0 type problem. And it is eligible for L'Hopital's rule. So all I need to do is take the derivative of the top. What's the derivative of the top? Come on, guys. What's the derivative of cosine? Negative sine x. And the minus 1, that just vanishes. What's the derivative of x on the bottom there? 1. Plug in the 0. The answer is 0. Don't you wish you'd had this tool on my first exam? I gave you a whole page of limits. You could have used L'Hopital's rule on every one of them. But you would have had no reason to believe it. Okay? Let's look at this next one. Maybe you know an identity, a special identity that gets rid of cosine here. Maybe you happen to know that this is 2 sine x cos x. Don't write that though. If you knew that sine 2x was 2 sine x cos x, the cos cancels out. Beautiful. But even if you don't know a lot of identities, L'Hopital's rule is going to bail you out. So first thing is just double check that it's 0 over 0 type. And it is. It's going to be sine pi on top and cos pi over 2 on the bottom. That is exactly 0 over 0. And then, once you've established that it is the right kind of problem, just run the derivative. So be careful here. What's the derivative of sine 2x? Yeah, it's cos 2x times 2 with that chain rule. And then we have cos x on the bottom. What's the derivative of that? Negative sine x. Good. And now you can plug in the pi over 2. So you get 2 times cosine of 2 times pi over 2 all over negative sine of pi over 2. You're getting 2 times cosine pi, 2 times cosine pi over negative sine pi over 2. Cos pi is actually negative 1, and negative sine pi over 2 is negative 1. So the answer to this problem is just simply 2. Who knew? Okay? Okay, let's look at the next one. So all I'm doing is just making sure it's L'Hopital ready, and then I'm just doing 2 derivatives. Derivatives are so much easier than anything else, right? I mean, this class is like, there's all these hard things to do, but taking a derivative is not a hard thing to do. Okay, let's try this one. I tried plugging in 0 earlier, and I got 1 minus 0 on top, which is 0, and I plugged in 0 on the bottom, I got 0. So this is definitely a 0 over 0 type problem, and we're ready to go. So the first thing I'm going to do is write this as 1 plus x to the half, right, to make it easier to take the derivative. Okay, so why don't I just pause the recording and let you try this one. And what's going to happen on this problem is you're going to need to actually use L'Hopital's rule 2 times in a row. After you get the first derivative, you'll realize that you can't solve the problem by substituting. It's still a 0 over 0. Then you're going to try L'Hopital's rule a second try, and then finally the problem will fall apart. Okay, so on the first time you take the derivative, it changes into this limit problem. 1/2, 1 plus x to the minus half, minus 1/2. You can just think of this as 1/2 x, right? Okay. You still can't really, oh, and the bottom's 2x. You still can't plug in 2x. You still can't plug in 0, though. You're still going to get like 0 over 0, and that's bad. So you just repeat yourself. You just repeat L'Hopital's rule. This new problem also qualifies for L'Hopital's rule. So you take the derivative again, and you get limit x goes to 0, negative 1/4, 1 plus x to the minus 3/2, all over 2. Notice the half is gone on the numerator there. And now you can finally plug in 0. And you get negative 1/4 times 1 to the negative 3/2 all over 2, aka negative 1/8. It's beautiful. What a great trick. This problem would be quite challenging if we had used conjugates. Yes?
You wrote
Oh, I wrote over 8 for no apparent reason. This should have been a 2, thank you. I know. Got ahead of myself because I knew the answer had an 8 on the bottom. That's my apparent reason. Okay, so I wrote a little sentence here for number 5. We can also use L'Hopital's rule more than once as long as we ensure that the problem continues to meet the conditions of L'Hopital's rule before differentiating numerator and denominator. Some call this the stronger form of L'Hopital's rule. So, in other words, it can be repeated. That makes it a very, that's like the strong way to learn it. Use it when you need it, even if it's midway through a problem where you just used it. Okay, this next one's probably, you probably don't need L'Hopital's rule on it, but it's kind of fun. It's definitely a 0 over 0 problem. So you would just go LIM, x goes to 0, take the derivative of top and bottom. You still can't really plug in 0, but it's not the same thing as before. Like, you cannot use L'Hopital's rule a second time on this problem. Can you tell me why? I said you can't use L'Hopital's rule unless it's 0 over 0, right? What is it right now?
1 over 0.
It's technically 1 over 0 when you plug in. So don't use L'Hopital's rule a second time. It's invalid, okay? Instead, you're just going to have to wrestle with this and what it means. So this is basically, look, I'm going to plug in a small positive number like 0.001. Well, the top is going to come out very close to 1, and the bottom is going to come out very close to 0. So let's say you plug in 0.001. You're going to get something really close to 1, and it's divided by 0.002. And that means this is getting big, really big. And it's technically going to positive infinity. So we don't usually write this, we just think it. You're like, what would happen if I plugged in 0.001? And you say, well, the bottom would be terribly small, and the top would be getting close to 1. Yes, a big number on the, or tiny, tiny number on the bottom makes it explode to infinity. Okay, so that answer is actually infinity. Same thing with this next one. You're doing LIM, x goes to 0 minus, and it's cosine x over 2x. And you could think, what would happen if I plugged in, 0.001, and it's going to come out close to 1 on top. And you're dividing by something very small and negative. So that one goes out to negative infinity. Again, I just want to state this. Don't write this, just think it, or do it on the side of your paper, but don't include it in your proofs, Okay.
Is there a specific reason not to do that?
You're not supposed to put approximations in the middle of your whole piece like that.
Which kind of could lead you to say something not.
Yeah, and we're technically supposed to be using not just 0.001, also 0.0001, and judging what's happening. So I'll continue recording. Watch the video tonight, or start in on the homework if you didn't do the curved ones, arc lengths. Okay, and then one more comment on this example before we leave it. What's going on in this problem is we're discussing f of x equals sine x over x squared. And what we're saying is there's definitely an asymptote here at 0. You could tell because when we did the limit on the right, we got infinity. And when we did the limit on the left, we got negative infinity. So the limit at 0 doesn't exist, but the two one-sided limit questions had meaning and had an answer. Okay? So that's kind of what it looks like on either side of the function. I know there's an asymptote at 0 because I got infinite values when I did a one-sided limit. Even if only one side had come out to be infinity or negative infinity, I would have concluded that there's a vertical asymptote at 0. Okay? All right, let's go to the next problem. Okay, one of the sort of surprising elements of L'Hopital's rule is that a problem that is written as not 0 over 0, but some of the other weird cases like infinity over infinity, or 0 to the infinity, or infinity minus infinity, or infinity to the 0. These are strange things that we don't totally understand. Anything that's written like that in L'Hopital's rule problem in disguise. Okay? So for example, this next example, example 8, isn't technically 0 over 0 per se, but it is actually infinite on top and bottom. Okay? So let me show you why it's infinite on top and bottom. If you take any number near pi over 2 and plug it in to secant, you're going to get a value of x, a value of y that is extremely large. So let me show you why. The graph of secant, you remember, looks like this. Here's pi over 2. Secant actually looks like this. So if you're near pi over 2, the graph is climbing up, see? And the bottom here, that's the 1 plus tan. That 1 plus tan graph is just a raised tangent function. It looks like that. But you can see that the two arrowheads are both going to infinity, not to 0 near pi over 2. So we would call this more of an infinity over infinity type problem. Now you'll also notice that it doesn't tell us which side of pi over 2 we're technically on. So that means that we're going to have to basically split this into two problems. A limit on the left, LIM x goes to pi over 2, left, and then sec x over 1 plus tan. And an entirely separate problem for the right side, like this. Now our work will probably feel the same, but we're kind of obligated to split this up because if you look on the other side of pi over 2, the secant graph, which is the blue here, and the tan plus 1 curve, which is the red down here, these graphs have arrowheads going down. So we have double up on one side and double down on the other side. So we feel like we should really separate this into two problems. We have different behaviors on either side. So is this problem like it does not exist? Like, what is this thing? Well, once you've written it in infinity over infinity, or negative infinity over negative infinity case, you can now use L'Hopital's rule to continue pursuing this problem. So now I'm going to go and take the derivative of top and bottom. So LIM x goes to pi over 2 left. The derivative of sec is sec x tan x. And the derivative of 1 plus tan is simply sec squared x. So this cancels out. And now you have tan over secant. Tan over secant is really just sine, because tan x is sine x over cos x, see? And secant is just 1 over cos x. So here's what you have. Let me erase this word and draw a line instead. So what we have is LIM x goes to pi over 2 left of sine x over cos x all over 1 over cos x, and then you can see clearly that this cancels out. All right? So in a limits problem, we do cross things out algebraically whenever we can. And this gives me the very simple question, what happens to sine x when I get to the left of pi over 2 and I get close to pi over 2? Well, it goes to 1. Now this next part of the problem is more of a negative infinity over negative infinity type problem. And you can see that's because our two arrowheads are double down. So they're both going down on this side. All right? So that will only affect us if we have to plug in numbers at the end. But this problem, like the last one, also crunches down all the way to sine. So following the same logic as up above, this all basically collapses into just simply sine x. And we can see that LIM pi over 2 from the left on a sine x graph is still 1. So this is very interesting, but the answer to this problem is actually 1, even with the asymptote there. So what is this? Why is it happening? What's going on? We're saying that basically, if you look at the left side, that's this part here that we circled. I just put a flower around it. The y-coordinates on this side, the ratio is getting closer to 1 as you get closer to pi over 2. So the red divided by the blue curve, the blue divided by the red curve is getting closer to 1. On the other side, these are both extremely negative down here, but the ratio of their y-coordinates is getting closer to 1 as you come in from the right. So on both sides, we're getting a value 1. All right? So it's interesting how we split that up, and we came to agreement. Interesting on that.